Something extraordinary has just been found in the moon's soil. Actual crystalline hematite and Maghemite, minerals that shouldn't exist in the moon's oxygen-starved environment. This discovery from China's Chang'e-6 samples challenges decades of lunar science and reveals a hidden process that may have reshaped the moon's surface. In this video, we uncover how scientists proved it, why it matters, and what this breakthrough means for understanding the moon's deep history. The discovery starts with something scientists did not expect to see on the moon: tiny, perfectly formed crystals of hematite and Maghemite preserved inside lunar soil grains. These minerals are normally associated with environments where oxygen is abundant, yet the moon is famously airless, extremely dry, and chemically reducing. Their presence in samples from China's Chang'e-6 mission immediately caught the attention of researchers because it directly challenges what we thought we understood about lunar chemistry. The Chang'e-6 spacecraft collected material from the South Pole Aitken Basin, one of the oldest and deepest impact regions in the entire solar system. These samples were brought back to Earth in 2024, offering the first physical material ever retrieved from the moon's far side. A scientific team from Shandong University, the Institute of Geochemistry at the Chinese Academy of Sciences, and Yunnan University conducted detailed laboratory examinations using electron microscopy, electron energy loss spectroscopy, and Raman spectroscopy. These methods allowed them to confirm the mineral's crystal structures, oxidation states, and micrometer-scale textures with extremely high precision. The analysis clearly showed that the hematite and Maghemite grains were native lunar materials, not introduced through contamination. Their shapes, chemical signatures, and nanoscale structures matched the characteristics of iron oxides formed under extreme temperature conditions. This finding was published in Science Advances, marking the first verified sample-based evidence that these high-velocity iron oxides exist on the moon. Understanding how hematite formed on the moon requires exploring a process that seems impossible at first glance. The moon has no atmosphere, no liquid water, and minimal free oxygen, so traditional oxidation cannot occur. However, the new research reveals that massive impact events in the ancient South Pole Aitken Basin briefly created the perfect conditions to generate oxidized iron minerals. When a large asteroid collides with the moon, the energy released is enormous. Temperatures can rise high enough to vaporize rocks and break apart mineral structures. The study suggests that during these extreme events, certain lunar minerals, especially troilite, underwent decomposition due to intense heat. This reaction released iron and sulfur, while oxygen bound inside other minerals was momentarily freed into the surrounding vapor plume. This created what scientists call localized high-oxygen fugacity environments. These pockets existed only for extremely short periods, but contained enough available oxygen for iron atoms to convert into ferric ion, the oxidized state necessary for hematite and Maghemite. As the vapor plume cooled, microscopic droplets and vapor phase particles condensed into solid crystalline grains that eventually settled back onto the lunar surface. The Chang'e-6 samples support this scenario because the hematite and Maghemite grains are incredibly small, only a few micrometers in diameter, and display structures typical of materials formed during rapid cooling. Their textures indicate a process driven by vapor condensation rather than slow chemical alteration, matching what would be expected in a high-temperature impact plume. The identification of hematite and Maghemite in Chang'e-6 samples reshapes several major scientific perspectives about the moon's evolution. First, it challenges the long-held assumption that the lunar surface is entirely reducing. For decades, scientists believed iron on the moon remained in lower oxidation states because there was nearly no oxygen available to transform it. Second, this discovery may help explain the mysterious magnetic anomalies detected near the South Pole Aitken Basin. These patches of unusual magnetism have puzzled researchers because the moon no longer has a global magnetic field. Hematite and Maghemite are capable of carrying remnant magnetization, and their presence in this region suggests they may contribute to these magnetic signatures. Third, this finding provides fresh insight into the role of ancient impacts in shaping lunar chemistry. If massive collisions could create oxygen-rich plumes capable of oxidizing iron, they may have influenced the formation of other minerals and altered the moon's surface composition in ways not previously recognized. This highlights the importance of impact processes not only in shaping lunar topography, but also in driving temporary chemical transformations. Fourth, the discovery demonstrates the immense value of far-side sample return missions. Remote sensing has limitations, especially when detecting small-scale minerals like micrometer-sized hematite. Having physical samples allows researchers to use advanced laboratory tools to uncover details impossible to observe from orbit. The discovery of micrometer-scale crystalline hematite and Maghemite in the Chang'e-6 samples from the far side's SBA basin is not just another lunar headline. It fundamentally rewrites assumptions about the moon's chemistry and magnetic history. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching, and see you next time.